All right. Hi, everybody. I think we'll make a start now. So welcome to those who are new to Malaysian Research Insider, and to those who have joined us last Saturday and the weeks before that, welcome back. My name is Alia Marzuki, and I'm a PhD student in psychology, just like our speaker today. So this science chat, as always, is co-organized by Malaysian bioscience scholars, 100 Scientists of Malaysia, along with our media partner, Science Media Center Malaysia. And today's scientist with me here is Anthony. He is a second-year PhD student in the University of Nottingham, UK, and his work deals with vision loss in patients who have had strokes. And he's also a co-founder of 100 Scientists of Malaysia. So without further ado, over to you, Anthony.
All right, thanks, Aliyah. That was a really good introduction. And hi everybody. So today I'll be talking about sight loss after stroke. And hopefully, it's an enjoyable experience. I have a lot of cool pictures of the brain, and I'll skip all the boring math stuff because, I've done those talks and people fall asleep in between. So let's hope this is interesting. All right, let me try to share my screen now. All right, did the screen come up?
Yeah, it looks good.
All right, cool. So today I'll be talking about sight loss after stroke using brain imaging to guide rehabilitation. My name is Anthony, and I'm doing this as part of Malaysian Research Insider. So let's begin. If I can move it to the next slide. All right. So I'm going to start with a quick introduction about myself. I'm going to talk about what sight loss is like after stroke. Some techniques we use in brain imaging, show you some cool brain pictures, and talk a bit about is there a marker for recovery? Is there anything we can do for these stroke survivors? So I actually did a bachelor's of science in psychology back in University of Nottingham, Malaysia campus. It was a good time. I learned a lot about psychology. And I actually wanted to be a clinical psychologist at first. After my undergraduate, I actually worked with special needs children for a year. And I think in that time, I kind of missed the research environment. I didn't think I would like it as much as I did, but after being away from it for a while, I actually, kind of missed it. So I went back to do my master's in brain imaging in the University of Nottingham, UK. And it was a really good time. And by chance, I actually met my supervisor while I was doing my master's. And he talked to me about this project he was applying a grant for. And as soon as he told me about a project, we'll be working with stroke survivors with sight loss. It'll be clinical work. It'll be meeting with stroke survivors. You won't be stuck in the lab all the time. I fell in love with it. So I was like, yep, sign me up. So I went up to apply for the application, and yeah, here I am 2 years in. And hopefully, it's an enjoyable experience for you to hear about what I've been doing so far. And I'm also a co-founder of 100 Scientists of Malaysia. And hopefully you've heard of this platform. We feature scientists from various fields to increase awareness of STEM and visibility of the Malaysian voice. And one small note, my funding body is Fight for Sight. It's an eye research charity. And without further ado, let's begin with the talk. All right, so sight loss after stroke. So right now you see a low resolution picture of a natural scene. The reason why it's low resolution is because my laptop couldn't handle any computation higher than this, and you'll see why. So hopefully everyone has seen a natural scenery like that. But if you've experienced some kind of sight loss due to brain damage or stroke, you might see something like this. So this person might have something known as right-sided hemianopia. So what is that? So you can see the right side of the image seems to be blacked out or grayed out in this case. But it's really hard to depict what sight loss looks like for someone with this condition, because it's kind of like trying to look out from the back of your head. So picture if you can see all the way to the back of your head, and now you can't, which is like everybody. Try to imagine that for your right side. it is really hard because, this is what we have in our heads, right? We reconstructed whatever we see in our head. So it's really hard for you to imagine a world where you lose the whole right side of your field. But that is what it is. Essentially, what you have is a sort of like a shrinking of your entire visual field. And which I'll talk about a bit more later. A lot of them don't realize they have this condition until later on, because it's not like a blind spot in your field. It's literally a shrinking of the visual field. The age of it still feels like what you have right now. So it's a really weird condition. All right, so yeah, the condition known as homonymous hemianopia, quite a tongue twister. It took me quite a while to be able to say that eloquently. So yeah, quiz time. So right now you see a picture of your brain with two eyeballs looking at the picture. So is the sight loss affecting only the right eye or both eyes? What does everyone think? So it's a bit of a tricky question because, commonly a lot of people imagine, one or the other. So let's take a few seconds for people to vote. All right, looks like we have so far 25% on for right eye and 75% on both eyes. So, all right, still about there. I see both is slightly pulling ahead. All right, I think we can end the polling. So yeah, so actually the right answer is it's both eyes. It's really weird because it's not intuitive to imagine. So you imagine it just affects the right eye, and actually a lot of the stroke survivors actually think they have their right eye is impaired. That's why they can't see out the right side. But what you do notice is that when you check both eyes experience the same level of sight loss because it's a stroke. It's due to the stroke damage. So let me show you a clinical picture. So what we see right here is what you can get at any opticians. So this is called a visual fields test. So just to make things clear, this is unfortunately a left-sided hemianopia instead of the right-sided hemianopia I showed before, because the patient I worked with just so happened to have this condition on the left side. So whatever you see right now, let's say the left eye, the black sections are denoting the blind view and the white sections are denoting seeing view. And you can see for both left and right eye, both eyes are affected by the same condition. So it's nothing to do with, if your right eye is damaged or your left eye, both eyes will see the same, even if you close one of them. So it's a very interesting condition, and it's kind of counterintuitive.
Anthony?
Yep.
Sorry to interject. Some people in the chat are saying there's a black square on your screen.
A black square. Oh, yeah. I think it's the poll.
All right, okay. All right, it's good now.
Yeah,
right,
Zoom has a weird bug with that. I've noticed that. All right.
Okay, great.
Hopefully the black square isn't you starting to experience some kind of sight loss.
All right, it looks good now.
All right, let's see. I've lost control of my slides now. All right, great. Okay, so, and another thing, it's commonly mistaken that sight loss is due to damage to the eyes. So a lot of stroke survivors, and I spoke to a few of them, they actually don't realize they have this condition maybe till like a few months after they left the hospital. And then one day they might bump into someone on the right or left side, or they might be driving and they completely miss a motorcyclist like driving past them. And that's when they suspect something is going wrong. So they see an optician, and the opticians would check their eyes, and they will find, oh wow, you can't actually see a huge part of your visual field. And then the opticians will check, and they notice they had a stroke. So they'll send them to ophthalmologist who knows more about the visual cortex in the brain, and they'll find out that it's actually their eyes are perfectly fine. The opticians will find nothing wrong with the eyes, nothing wrong with the retina. But what happened was that there is a stroke damage, which happened kind of past this crossing, you see. So let me just get the laser pointer. Right, never mind, I can't get the laser pointer out. So wait, all right, yep. So if you see right here, this is crossing. So just to mention, if in case people not unsure about it, the right side of the brain governs the left eye, and the right eye is governed by the left side of the brain. So if the damage occurs past this crossing, you will have this condition known as anomalous hemianopia or quadrantenopia, which is a different condition. But yeah, so anything past this point, it will affect both eyes equally and is caused by stroke damage to the brain. So if you see the stop sign, basically, information from both eyes can't enter the left side of the brain. And that's why you completely lose the right side of the visual field. And it's quite scary when you think about it. You know, this affects not only driving, walking around, people struggle to read because you can imagine that it's so annoying to read when you only have like half your visual field. You have to make constant eye movements, and it's it's very debilitating. And we do notice that a lot of people with this condition tend to fall a lot. Stroke usually affects older individuals, and when you lose a huge part of your vision, you tend to fall more often, and it's really bad. Like the risk of falling is actually quite a big predictor of the quality of life when you hit 60 or 70. All right, so we talked a lot about like what vision looks like, but let's look at the brain. So right now I have a 3D image of the brain. So usually when I do this talk live, I will bring some 3D glasses, like the red and blue ones. Unfortunately, it's a Zoom presentation and I can't mail the glasses to all of you. So if you do have one, bring it out. This actually pops out. But you can see right here, let's wait for the brain to spin around. It's coming. All right, so right here, you can see there's sort of like this hole in the brain. So it's quite a sizable chunk gone. And yeah, like it's quite scary, I think. Like I've met a lot of stroke survivors with a huge chunk of the brain gone, and you don't notice anything wrong with them. They speak perfectly fine. They can write, they can talk, but it's only when you do like this magnetic resonance imaging that you find that actually a huge part of their cortex is missing. So yeah, so these are the still images. So right here you see this gentleman with quite a significant loss in the visual cortex. So from the top view, you can see like at the back, it's just completely gone. And yeah, this person has a right field hemianopia. So just to add more confusion in, radiologists like to put the left on the right side and the right on the left side. And I've been caught out a few times messing this up. So yes, it is. This is on the left side, even though it's on the right. So yeah, it's a bit confusing. And yeah, and if you look through across a few stroke survivors, one thing you notice is that the brain damage varies quite differently across all of them. But funnily enough, it doesn't actually predict what kind of visual field loss you might have. And this is one thing our lab is trying to look into. It seems like the textbook example of what kind of damage affects what kind of sight loss isn't entirely correct. It seems like there's something else driving the sight loss, and we're trying to look into that. So if you just try to look at the different pictures of the brain, you notice that the damage is so different. Like some of them are extremely large, some of them are a little smaller. So it's pretty interesting to look at these images and for us to kind of answer that question, what is causing the sight loss and what parts of the brain are more important in driving our visual fields, what we see in our visual fields. All right, so there was a poll previously about who has been an MRI machine before, the magnetic resonance imaging. So yeah, it seems like a lot of people haven't, and honestly, I wouldn't recommend it if you don't have to. It is not the most comfortable position to be in. What happens is that they run this really powerful magnet. So this magnet is 4 times more powerful than a magnet that can pick up a car. So yeah, just think about it. That is a crazy amount of power. And yeah, so we use a 3 Tesla magnet to do this imaging. And what it does is that it kind of shifts the magnetic poles back and forth, and it sorts of creates these images of the brain we see. And it's really cool. It's really complicated how the physics and like the chemistry of the brain kind of work in conjunction with it. But yeah, you get this. What you get is a really loud pulsing noise in the MRI. And if anyone's been in there, you know what I'm talking about. It's really annoying. It's really loud and not comfortable at all. But yeah, please do join if you are interested in doing research, because we need participants all the time. And yeah, most of us in Nottingham, we run our research in Sir Peter Mansfield Imaging Center. So a bit of a fun fact, Sir Peter Mansfield won the Nobel Prize for his contribution to the invention of the functional magnetic resonance imaging. So yeah, pretty cool. It's actually the birthplace of the fMRI. And his invention allows us to look at activity in the brain while participants or individuals are doing something inside an MRI. So it opened up the field to learning about, you know, functional activity in the brain, activity across time. It's it's a really interesting work. And yeah, apparently it's quite nice. It is a really nice building and a lot of friendly people working in there. So this is a reconstruction of the brain right here. And just to give you an idea of what our stroke survivors see inside, once we put them into the magnet, they see sort of this contrasting circle, this sort of hypnotizing pattern that goes in a cyclic manner. So the idea of this picture is to sort of try to kick every neuron in the visual cortex to activate. This is the most sensitive visual information you can send to the brain. So because we know that they've experienced some kind of damage to the brain, we want to use the stimuli that would like be able to activate any part of the neuron. So we're trying to fire everything we have and hoping that we see some kind of activity in the brain. And if you take a look at the right side of the slide, so we have the left hemisphere on the left and the right hemisphere on the right. So like I've mentioned before, the visual field on the right side is governed by the left hemisphere. And funny enough, even though they mentioned they can't see anything on the right side, if you take a look at the left hemisphere, you see quite a bit of activity. So it's kind of weird, right? Like you would expect no activity in the left hemisphere considering you can't see anything. But that's often not the case. Our lab's not the only one to find it. Labs around like the world have found this weird phenomena. And it's also known a different name, known as blind sight. So some of you might have come across this term where even though they're blind on one side, if you kind of shake your hand through there, they can tell something's moving. So clearly the brain is picking up something. So maybe what we think about sight loss isn't exactly correct, or maybe what the clinicians are using is not the most sensitive measure. I mean, all they do is they shine a light at different parts of the field, and if you say no, then you're blind. So maybe what the brain is doing, it's picking up different kinds of visual information, and it's actually still working, just not the way we think it does. So our lab feels like this could be a sort of marker for recovery. If we do find these signals in the stroke-affected brain, maybe we could train it to be able to see again. So here we have this picture. It's called we call it a visual field coverage map. So what we do in our lab is we recreate using the activities you see in the last slide, and we reconstruct them to this sort of visual field coverage map to represent what that part of the brain sees in the visual field. So we use this technique, this complicated name technique known as population receptive field analysis. So yeah, quite a mouthful. Yeah, so the idea of this technique, which I won't go into, I'm just briefly talk about it. We're trying to use this model to guess this part of the brain, where is it looking in your part of the visual field? So it's sort of this repeating pattern. So it checks this part of the neuron, let's check if this field works. If it doesn't, we'll check a different spot of the field. So we keep doing that iteratively until we get this really nice image of what the brain sees. So let's map out that scenery you had. So remember with this individual, they couldn't see out the right side. But when we look at the left hemisphere, it seems like a big part of the brain still reacts to the information. So maybe, you know, the brain is picking up something. Maybe the neurons are suppressing it because the information is not clear enough. We don't know. The real answer is we don't know. But the thing is, we do find these results, and that means that, you know, there are more questions to ask. Why is it the case that they're blind on the right side? You know, even though the brain is picking up information, what kind of information can they pick up? Is it motion? Is it shapes? Is it, you know, large scenes? We don't know. So our lab is trying to tease that out. And the bigger question is it different across people? So a big part of why stroke research on stroke damage is so difficult is because stroke affects everyone so differently that there is no one way to solve this problem. So our lab is trying to use this thing known as sort of personalized rehabilitation, where the rehabilitation is developed based on the stroke survivor themselves. So it's completely unique to each person. So our idea is this is the best way to treat these kind of damages. So how do we do it? That's the big question. So this is what our lab has came up with so far. So we know that this part of the brain is activating, despite the person not being able to see out this area. So what we do is when we select the area and sort of create this this is known as a Gabor pattern, but you can think of it sort of like a patch. And we kind of show that really contrasting pattern on the screen. And what we do is that we show two frames. One frame would be an empty frame, and the next frame would have the pattern. And you, if you're a stroke survivor and you're doing this rehabilitation, you would have to tell us, was it the first frame or the second frame that you see the pattern? So you can guess that, you know, you'll get it 50% chance right, you know, of in each trial. But the really funny thing is, when you test an area with the visual field coverage, you find it goes from chance performance all the way up to close to perfect. And that's pretty crazy. You know, once again, I'd like to remind everyone, they can't see out that area. You know, this person still can't see. And we asked them, you know, after the training, can you see out the area? And they can't. But what they do mention, which is an interesting thing, is that they're starting to see a ring of light around the area. And that's really interesting. You know, it's a really weird phenomenon. And to control for it, we've actually also tested in an area without the visual field coverage, and we don't find any significant improvement. So clearly something is driving this activity in the brain. So this comes to the part where I need to talk a bit about how COVID-19 has affected this research, because unfortunately about all those big plans we talk about might have to be postponed for a bit, as yeah, stroke survivors are within the high risk group. So there's a good chance we will not be able to test them in the near future. So our lab's actually shifting to a sort of a more mechanistic understanding of the problem. So a lot of work has been done to actually simulate these kind of conditions, because even before COVID, it was really hard to recruit stroke survivors with this condition, because it is such an insidious condition. Like I said, a lot of people don't realize they have it until, you know, they bump into someone. I actually know this lady who only found out after she was bumped onto the floor, and she noticed that she had bruises all over her arms, and she didn't know why, because, you know, like you don't realize that you got bumped into until it hits you. And that's really scary. You know, a lot of them, they feel after having this condition, they find that the world is really scary. You see, you basically just, you're blind on one side, but you can still see the world. It's a really weird feeling. So we try to simulate it. So one thing we're trying to simulate is, how do people read when you have this condition? So if you see right here, you see a you know, so text, you know, animal and plant that live in areas with cold, blah blah blah. So yeah, this is a text that you might read in a book. And what we do is that we use the computer to sort of simulate this sort of blurring effect. So what happens is that it tracks your eyes, and from that center, one half of the screen will be blurred depending on the left or right condition. So in the right condition, it'll blur the right side. And the cool thing is, as your eyes move, the blurring will follow it. So the idea right now is not to, you know, some labs are actually just blanked out the left or right side, but that's not the case, right? We do know there is some information coming in, it's just not the full information. So our idea is that by degrading the information that enters that side in several levels, we can sort of model this to fit to the behavior of stroke survivors with this condition. So the idea right now is to simulate as close to what we know about sight loss, but not trying to say we actually can simulate it, because it's impossible. So that is our current work right now. We're going to try to, I only have one more year left in my PhD, and we're going to try to simulate this sight loss, and hopefully what we do find about the behavior will help guide rehabilitation in the future when the COVID crisis ended and we can start inviting stroke survivors back in again, and so we can, you know, guide the rehabilitation. So yeah, thanks so much for listening to my talk. Hope I didn't ramble on too much. I'd like to thank a few people in my lab. Ben Webb and Dennis Schlupek are my supervisors, and a couple other people who worked on this project with me. And yeah, hopefully that was interesting.
Okay, cool. Thank you so much, Anthony. That was a really, really interesting talk. And I just want to commend you for being able to bounce back so well from COVID interrupting your research. I think it's really cool that you found sort of another niche that your research can fill, despite these plans going awry. So that's really cool. Thank you for that. And
Thanks.
so we'll move on to some questions now.
All
What
right.
we'll do
Oh, I
is
see quite a bit.
yeah, there are a few questions. A lot of people are very interested.
Okay.
We will do some general questions first, and then we'll move on to the more specific ones. So first, a question from Hakeem. I think he wants to know a bit more about what the damage entails in the brain. Is it nerve damage when it comes to what is causing the sight loss in stroke patients?
So most commonly is what we do find is ischemic stroke, where it cuts off blood in one of the vessels that connect to the visual cortex. And well, when you cut off blood to the cortex, basically the neurons die. And yeah, basically it's neuronal damage, and the brain, the section of the brain kind of shrivels up, and because it doesn't get the nutrients from the blood, and it just dies off. So you get this over time. It's kind of like just empties out the area.
Mm-hmm. And what exactly triggers this? Is it an age-related thing? Are you more prone to this blood loss?
Yeah, we do find that there is a correlation with age with stroke. To how much to how much it's a causal relationship with age, it's still up for debate, because there's dietary habit, exercise, sort of like daily rituals and habits. So I would say I'm not the right place to give an opinion on that, because I'm not a stroke researcher. I mean, I'm not specifically a stroke researcher.
Mm-hmm. Yeah, it's more on, I guess, the simulating sight loss based on vision loss in stroke patients, right? Yep.
But one thing I can say is there is an interesting phenomenon where after getting the sight loss after stroke, there is a small chance that within 3 months, you'll recover and it's as though you never got the sight loss. It is known as spontaneous recovery, and it happens quite a bit. So a funny thing in the literature is that it kind of messes up the prevalence of sight loss after stroke, because you have doctors who define these disorders at different time points. So sometimes they have it, sometimes they don't, and the rates go from 20% to 50%. So it's feels a bit crazy right now.
So that's really interesting, the fact that you can have spontaneous recovery from stroke. Yeah. So when people undergo this spontaneous recovery, if you do know this, does that part of the brain also seem like it recovers, or is it some sort of, how do you say, is some other part of the brain maybe making up for that damage and acting as the sight
That's
area?
a very good question, because our lab is basically banking on the idea of plasticity in the brain.
Yes.
I don't know for sure, because spontaneous recovery is really hard to study because it's random, like we still don't know what determines when you experience spontaneous recovery. But what I can say is that oftentimes, especially in older individuals, the brain becomes less plastic as you age. So it's unlikely that within a short frame of time, the brain adapted so quickly that it could fill up the sight loss that you experience. More likely is that the stroke damage wasn't widespread enough to take out the cortex responsible for your visual field, and it sort of recovered, as per usual. If it took out the whole cortex, it's unlikely that the brain adapted that fast.
Makes sense. Okay, and another question from Hakeem. So the exact missing part is the visual cortex, yes? The visual center?
Yep. So there are multiple areas where it could affect. It could affect the optic chiasm, sort of the different parts of the visual pathway. So this condition specifically happens post lateral genital nucleus. If it happens in different parts of the visual pathway, you would see sort of different types of visual field loss. Sometimes they are quarter the vision, sometimes they're opposite sides of your eyes. So one eye will experience right visual field loss, the other eye will experience left visual field loss. So there's a textbook on it, and you can kind of see the different conditions it will create. So yeah, it depends. It's actually quite interesting field. Like visual field loss is so diverse, and we still don't really understand what are the determinators. We only have clinical studies.
Makes sense. A question from Pei Chin. So you had a picture of sort of a brain, and you mentioned that this part is, even though it's on the left, it's on the right, and this part is on the right, even though it's showing it's the left. So they're asking, why exactly does the radiologist flip it this way? Is there
That's a very good question. I asked the exact same question when it came up because it kept messing up my my calculations.
Yeah.
The reason why is because the stroke the participants usually lie in a supine, sort of like they lay down, and then because of that orientation where they determine that side to be radiological left and the other side to be radiologically right, it's just because of how they lie down in the scanner. Why did they not switch it around? Either go back to the guy who invented it. I don't understand why he decided, okay, you know what, I'm going to mess everything up. Left is right, right is left. Let's hope everyone makes mistakes in the future.
Make things more difficult for everybody.
Yeah, I've made that mistake quite a few times so far.
Yeah. Okay, so this is a question from Duncan. If you image the brain for one individual when they're doing something, so I think this refers to the part where you were showing participants in the scanner the fan-like visual test that goes around the screen. So if you image the brain of that one individual when they're doing that particular task, how applicable is that data you collect to any other person in the population? I think because also you mentioned that stroke damage is very heterogeneous. There's lots of variations in how stroke damage can be shown in the brain. So how applicable is that data you're collecting?
So that's actually a really good question. So the idea of the image is that it is very sensitive to the visual cortex. And the idea is that if the prior understanding is that there is no visual information entering the brain in that side of the brain, to disprove it will be to find any kind of activation at all, and we control for the activation. So we're making sure it's not noise, it's not smearing across from the other hemisphere. So the fact that we do see some kind of activation, it means that the brain is picking up something that for some reason, even though you can't see out that side, something from the visual pathway is still activating some of the neurons in there from the sort of residual areas.
And is that true across all the patients you've tested, or is there a certain percentage of people who experience this sort of seeing something even though they can't really see it?
So yeah, that's another good question. Because we don't have that many samples, I can't give a percentage, but it's right. Not everyone has this. If in the case where the entire left visual cortex is taken out, you can't recover anything. If the machinery is not there, there's nothing to recover.
There's nothing.
So it only works if you have some kind of residual cortex and it's, for some reason, it's picking up some activity, then it may be a marker for recovery. But to what extent you can find recovery, that was our initial plan. And hopefully it'll be someone else's plan once the COVID crisis has
for sure
subsided.
Because you mentioned that different people have sort of different specific empty spaces in their brain when they experience a stroke. So does this differ by age, I think is the question they're asking.
I would say there's no pattern right now that we can observe, because it is, you wouldn't think that a stroke will affect someone the same way, because stroke right now is really sort of random in a way to what extent it affects you. So some people might come out with motor problems, some of them speech problems. We can't actually predict it. Not that I know any machine learning models out there that can have managed to predict it. But maybe in the future, we don't know.
Yeah. Yeah, there's lots of promising research for the future, definitely, in this field.
Oh yeah. On a small tangent, I'd like to share this. I actually read about this early in the year. Someone actually managed to recover the visual pathway in rats. So what they did in their lab was that they pinched off the visual pathway in rats, and they used stem cells to and what they found was that the blind rat was able to see after the stem cell therapy. So what happened was they pinched off the optic nerve, And with stem cell recovery, the nerve grew back. So they did this in rats, and it was crazy. They tested it again and again to make sure this is right, because this is groundbreaking. The fact that they recovered, they regrew a nerve, a really important part of the visual pathway, and it works. So
That's really
who knows? Maybe this can be applied to people. It could cure glaucoma, macular degeneration, and maybe hemianopia.
Yeah, that's really cool.
So yeah, small tangent.
Yeah, no, it's a really cool study, and it kind of ties in with what you said about brain plasticity, and things growing back and things maybe moving to another part of the brain. So the next question is, so again from Hakeem, I guess this is more to, how there's a blind spot in in healthy people's eyes. There's a blind spot, right? So they ask, isn't the brain good at filling gaps in information, because whenever that information falls in our blind spot? And they mentioned that, for example, when words are mostly recognized by the first and last letter. So I think maybe this is referring to, is that potentially why stroke participants are able to maybe see things even though that part is damaged?
So that's a very good question. So the reason why you have a blind spot is because that area is where the optic nerve is, and it creates a blind spot, but we don't notice that. Like how we don't notice our nose, but actually your eyes can pick up your nose. It just kind of blocks it off. So there is sort of a filling up going on, and this really cool thing that we observe is that a lot of the people with hemianopia, they often see things in the blind area. So I had this gentleman who saw, this lady in the purple T-shirt. Sometimes he saw Jesus Christ. We had a lot of stroke survivors who saw dead relatives in their blind spot. And I think what is happening is that they're piecing in this small little information they get from the visual field, and they're recreating it in the brain to solve something they're familiar with. So there is the idea that the brain could be using this information, and we have a theory going on that maybe higher up in the visual field, visual areas, that the brain is trying to piece together this sort of noisy visual information from the blind area and trying to conjure up something that makes sense. So in some cases, it occurs as a dead relative. But yeah, I guess it's interesting question.
Okay. I don't suppose you know much about the more molecular side of vision when it comes to, I don't quite understand.
So like ion channels or?
Yeah, probably. As in maybe when it comes to stroke patients, how do you kind of study the more molecular side, or how is it damaged on a molecular level?
I guess unless we can jab an electrode into the back of the brain, I don't think we can study that unless someone has came up with a different way of doing it. But yeah, so far I've not come across any research that puts electrodes into people's heads, but hopefully we can someday in some other way.
Maybe in animals? Has that been done before?
No. So far, in my experience, we haven't found any macaques, which is commonly used in sight loss research. Vision research that have this condition. Because, I guess it's quite hard to notice that a macaque can't see out of the right side of the view.
Yeah, of course, you can't ask them.
Yeah, you can't be like, hey, can you see this banana?
Yeah. Yeah. Is it, can you simulate stroke in animals? This is just a personal interest.
Actually, it's a good question. Maybe you can try to simulate sight loss by knocking out one of the vessels. But yeah, I haven't came across any papers that have done so. But yeah, it's a good question. It could be possible that you knock out the areas that you know causes sight loss in one side of the field and study it that way. But yeah, I've not come across any vision researchers that have done so. Yeah, that's a really good idea.
Okay.
But yeah, I'm not really into animal research. Not really my cup of tea.
Yeah, it's not my thing either. I tried it once and I'm like, no. So this is a question from Facebook. They were just wondering, are there any physical assessments from any healthcare professionals to assess hemianopia?
Sorry, could you repeat that? I think my connection kind of jumped a bit.
Oh, sorry. This question from Facebook. Are there any physical assessments within a healthcare setting for how you assess hemianopia?
So yeah, once again, another good question. Actually, a lot of stroke survivors are admitted out of the hospital without the doctors even noticing that there was anything wrong with their vision, because it is so insidious. When they wake up after these, after they send to the hospital after a stroke, it's very rarely you realize that something's wrong, because you just assume that maybe you're tired, maybe not turning your head around enough. It's only when something happens that you realize, wait, something's a bit different right now. I can't put my finger on it. So yeah, oftentimes it goes overlooked, and it's something that most doctors are not aware to check about, because it's not commonly, like, the symptoms aren't really that obvious.
Oh, sight loss, hemianopia isn't that obvious.
Yeah, because to see sight loss would be to bump into something by accident consistently.
Yeah. Okay, so does that mean hemianopia doesn't happen that often in stroke patients in this particular area?
So the literature seems to suggest like about a quarter to 1/3. But like I said, there's quite a lot of error with that prevalence rate because of how it's being diagnosed. So I would say conservatively, you should assume a quarter.
Okay. This is quite an interesting question from Muskan. She asks, does this sight loss affect their hearing or memory in any way, or is it just vision?
That's a good point. It doesn't affect the hearing or memory, but what you do see sometimes is that the stroke caused a damage to the motor area or the language center or the auditory center, along with the visual center, and you get this kind of comorbidity between maybe some kind of motor loss on the right side and a right field hemianopia. But yeah, it's not linked in sort of that like connection. It's just like the stroke caused these damages.
This is another very interesting general question. Does hemianopia caused by stroke affect the dreams of these patients? Do they see normally in their dreams?
That's a very interesting question. I've not talked to them about their dreams. Maybe I should ask them in the future if I do meet them. But I would assume no. Because like I said, it's very hard to describe what it looks like to have sight loss in that way. Even I myself took quite a while, and I actually have experienced some kind of sight loss before. I've lost the central part of my vision. It's sort of known as ocular migraine. It only happened once. And you just kind of lose this part of the vision, and it's not really obvious that it happens. You only realize when something's kind of off. So yeah, I might ask them in the future.
Yeah, I guess because when you're dreaming, you kind of, I don't know, like maybe you picture yourself as healthy in your dreams, because that's ideally, how you would want to be, right? Yeah.
I guess, I don't know, I feel like dream research has been kind of left in the dust after like move into like computation and more neuroscience work.
That's
Maybe
true.
we should take a turn back.
No, the only sort of reputable dream stuff I've seen is in animals, where rats dream about where they've moved in a maze and things.
Oh, okay.
Like, yeah, it's quite interesting. Like if you make them navigate through a maze and then you stop them from dreaming about the maze, they forget how to get through the maze. Like, that's quite cool. But if you allow them to dream, then they can't navigate the maze. So yeah, that's the only dream sort of research I've come across.
Yeah, but I wonder how that extends to like people, because we don't know what the rat is seeing in their dream. Like, do they see this random finger coming in, like, okay, no more maze for you?
I think it's more like the same neurons that fire when they're awake fire in their dreams. Yeah, but you don't exactly know what they're seeing. Yeah, exactly.
So maybe if you see like the visual cortex lighting up, because you would expect the visual cortex to light up, because we do know that when you imagine something, the visual cortex lights up.
Yeah, makes sense. So does hemianopia affect their perception towards shapes? Like, do they see properly in the visual field, or is it skewed? And how do they view people?
Okay, I'm guessing on the blind view, is it? Or on the seeing view? I'm not too sure.
It wasn't really stated in the question.
So on the seeing side, all of them tested normal, shape recognition, pattern recognition, orientation. So, okay, on the seeing side. So yeah, on the seeing side, perfectly fine, nothing wrong with their vision. So the eyes aren't affected whatsoever. And the healthy hemisphere, which governs the seeing side, perfectly fine most of the time. So we don't observe these kind of disorders.
But on the, I guess, on the non-seeing side, obviously you're obviously impaired there.
We're getting nothing into that side. So
in
the terms of their consciousness.
They just know something's there, but they don't know what it is what you tend to see. Is that right?
Sometimes I've talked to this person where she said that when she was walking through a crowd, she can sort of see people crossing through, even though she's blind. It's like she knows that something is coming, like this large figure is coming, looming across the view.
That's very interesting.
This is not everybody who feels that. So it's really weird. It's we don't know. We don't know why this is happening.
So this is from Sam from Instagram. Do you use any machine learning methods for image analysis?
All right, so that's a really good question. And the short answer is I would like to. It's because I'm not trained in a computational background. I have spent the past few weeks trying to pick up some technical skills on that. And the final year of my PhD, I will be trying to do something like that. I think there's a lot to gain from applying sort of this mechanistic understanding by modeling the neurons from the neural level to a population level to higher visual areas. So there is something to be said about that. To work out images, the reconstruction of what the brain can see, like from that slide with the population receptive view analysis, I think there could be more work to refine sort of what the brain can see. Because once again, like there are some assumptions to be made, we can still refine it. And it's still relatively new field. It's only been, I would say, at most 10 years old. And that's quite new in vision. Vision is a very old science.
Yes. Okay, very cool. So we're about wrapping up now. So this is a question that we always ask our researchers at the very end of the talk. So what are your career aspirations after your PhD? Where do you see yourself heading after this?
So I think with my aspirations, I'm kind of looking towards sort of a teaching role and with some research on the side. I still enjoy research, but I've come to find that I actually quite enjoy teaching too. And it's really nice. I really like the environment where we sort of be very supportive and open environment to pass on knowledge to other people, and you see your students sort of like acquire this confidence and knowledge about the field. It's really nice. I also see myself kind of working towards, I'm part of a team of that founded Scientists of Malaysia, and we want to try to sort of bring some change to the education system and the STEM fields in Malaysia. I think Malaysia has a lot of opportunity to grow. We have so many talented individuals from different kinds of backgrounds, different fields. I think with my experience, and I can say for my team too, I think we were also ignorant to some of the different fields in Malaysia. We started out thinking, we need to show diversity, but when we started this project, we came to see more and more different views and different niches in Malaysia. And you'll be surprised how many scientists we have in Malaysia. It's crazy. And I would say the average person doesn't even know like 0.1% of them.
Yeah.
So yeah, it's I do look forward to working more towards that goal.
No, that's a really interesting point, because I think, especially when you study overseas, you sort of get to know the different fields that are important overseas, like in Europe, in Australia, in America, that you don't really think about the fields that are important in a Southeast Asian context, right?
Oh yeah. Cultural differences are a huge factor, and yeah, it's really interesting to have sort of like an outside perspective now that I think allows you to see a different kind of picture, and I think there's a lot to be done with it.
No, that's brilliant. All right, thank you so much, Anthony. That was a really brilliant talk and a very illuminating Q&A session. Thank you very much for joining us today. And thank you very much to our audience as well for sending in questions and for joining us for the talk today. And we will resume Research Insider on the 22nd of August with Sean Wen, who's from the University of Oxford, and he studies cancer genetics. So for more updates regarding future Research Insider series, please like our Facebook page, and BIOS and 100 Scientists of Malaysia. Until then, thank you. See you on the 22nd of August. All right, bye-bye. Thank you all.
Thanks so much.
Bye.